Hello, this is Jan Verijn from Leiden University, and today we will be going over solving the traveling salesman problem with exhaustive search, and we will do some hands-on programming in Python to do this. The traveling salesman problem is a fundamental problem that is often used in algorithms, and you can see it in various forms. This video assumes that you kind of are familiar already a little bit with the traveling salesman problem, but here we see an example. Given a certain amount of cities, let's say n cities, that all have a distance towards each other, and this can of course be represented as a graph, find the shortest path that visited each city exactly once and return to the initial city. So you can also reformulate this as finding an Hamiltonian cycle in a connected weighted graph. And the reason that we're going to use exhaustive search for this, there's of course better algorithms than exhaustive search, but the reason that we're going to do exhaustive search for it is that there's currently no known algorithm that will always be efficient when solving the traveling salesman problem. So the moment you make the graph larger and larger, or you're going to solve larger problem instances, it will take always a long amount to solve this problem. We don't know of any exact algorithm that will always return the best possible answer that will terminate, will do something faster than exponential time, where the running time is exponential in the size of the graph. And here we see some possible routes that could be a solution to this instance of the traveling salesman problem. We see the route starting in A, going to B, going to C, going to D, going back to A, which would cost in this case 18 units, maybe kilometers, maybe euros, maybe minutes or something like that. And we see also some other solutions. For example, A, B, D, C, A is in this case the fastest, which cost 11 units. But we also see that all the routes here start in A, because we can also prove that if we just want to find a shortest route, we can always start in A, because a similar route would be found if we wanted to start in any of the other cities. So this is a property that we can use to make the algorithm a little bit easier or faster. Now, how are we going to do this? We're going to look at the state space in a bit on this particular example. And in this state space, a state is a list of cities that we have at that moment already visited. And we will see an example of that in a second. And the goal state where we want to be is we want to be in a state where we have visited every city in such a way that each city only occurs once. So this, of course, can be represented as a Python list, in which we keep track of all the cities that we have already visited. And in this case, if we have a state space diagram, we can represent every action as adding a city to the list that we already have. Some examples of states that we will have. So the list AD represents a valid state, but this is clearly not the goal state, because in this case we have been in A and D. But the list ADCB represents a goal state, because we know now from A we want to go to D, from D we want to go to C, and from C we want to go to B. And from B then of course we want to go back to A, but we don't of course need to add this to the list, because we can do this implicitly. We can of course also add this explicitly to the list, and it's of course up to us. But in my opinion, not adding this explicitly to the list results in easier code, but that's of course up to us later to do this. And the list ADDB, that represents an illegal state, which we should avoid coming in if we build our algorithm in the proper way. Now, what does this state space look like? The state space looks a little bit like this, where we have here our initial state, and from our initial state we can choose to go to first to A, or first to B, or first to C, or first to D. I've only drawn out here the state space that decides to go first to A, because of our aforementioned reasons, that this indeed was the most efficient way of doing this. And from A we can go to B, from A we can go to C, from A we can go to D, not to A itself again, because that does not make sense. And if we decided to go then to B, we could have chosen to go to C or to D. And also here we do not, or we avoid the state where we go back to A, because that is an illegal state. And by creating this tree in a smart way, we can of course avoid this. And also, as I already mentioned, if our goal is to find just a shortest route, we can of course also make the assumption that we want to start in A, because if there's a shortest route that starts and ends with B, that shortest route can also be constructed when starting and ending in A. So we can also look at the state space diagram in this way, where we only see the state space of A. And again, this is quite a small example, so this state space diagram is quite manageable, but if you start working with larger graphs, this state space diagram becomes larger and larger. Two more important things to note. Again, we already discussed this. Eventually, the traveling salesman problem is also about going back to the initial state. So actually here at below all the leaf nodes, actually what you want to do is also go back to 8, but of course this can be done explicitly or implicitly. That was one of the important things. And we're going to use this state space diagram to reason and to think about our code. But first, let's have a look at the framework that we have to create code in. And here I've already created a little function called TSP, Traveling Salesman Problem Brute Force, and it gets 2 arguments, graph in a form or representation, and I've in this case chosen for the adjacency matrix. We could of course also have taken the adjacency list, but in my opinion an adjacency matrix is in this case resulting in easier code. And I've also created an argument called state that keeps track of the state that we are currently in. And here we see I've already created a small test case below. This is the graph that we've seen before, so we already know the optimal answer of this graph. And I've made an initial call to this function where I call it with graph and with our initial state. Currently this is empty, but of course I could also have said we want to start in node A. Now, because we're working with an adjacency matrix, so this is the basically the first row and the first column represent the distances coming and going to node A. But this is in of course Python language represented as index 0 of this array. And I could of course create a mapping where I say mapping from matrix index to city name, and that could have looked a little bit like this, where I say, well, index 0, that is actually a city name A, and index 1, that's actually a city B, index 2 is actually city C, and index 3 is actually called city D. But to be honest, I cannot be bothered by this. I would actually like to prevent this, and in this case I will just assume that city A is represented in row 0, city B is represented in row 1, city C is represented in row 2, and city D is represented in row 4. And what I'm now going to do is I'm going to say, similar to what we've seen in this graph here, I'm going to say, well, we can always start with city A, because that is, and city A was represented as 0 in this case, and that was the proper, that always leads to an optimal solution because of the aforementioned reasons. Good, let's now look at how shall we implement this algorithm. So looking again at the graph, and this is quite common for all sorts of exhaustive search problems. We have here the state space tree, and of course this state space tree, we don't have access to it because this is implicit. Somehow we're going to implicitly visit all the nodes in this tree, but this tree itself does not exist. We're just going to in an algorithm, we're going to basically try all these options, but by going in a smart way through the graph that we've seen on one of the earlier slides. And basically there is two type of nodes that we have in this state space. We have a terminal node. So for example, when we have here the situation A, B, C, D, or A, B, D, C, basically then we do know from this state what the optimal solution is. So given the state A, B, D, C, then we do know, okay, if this is the state where we are we do know the optimal solution, because, well, all we have to do is in this case, well, calculate the distance from A to B, calculate the distance from B to D, and calculate the distance from D to C, and later again also from C to A. And then we know what, given this state, the optimal solution is, or given this partial, it's not a partial state, it's a goal state. But for all the other nodes that are not leaf nodes, the situation is of course not that simple. So for all the other nodes, for example, if I have A, B, D, then potentially there are still choices to be made. In this particular case, there's no choice to be made, because we can see in this tree that there's only one option, and then once we follow that option, we have the final solution. But of course, the algorithm typically does not know this. So for example, if we had the partial state A, B, then there was an option to be made, and basically we have to try out both options, namely, adding C to the state and figuring out what from there on is the best, but also adding D to the state and figuring out from there what is best. So basically there's two types of nodes, the goal state and the non-goal state, and we have to distinguish between what we do when coding the algorithm between those two cases. And let's first do this. So how do we know that we're in a goal state? Now we're in the goal state when the variable state contains exactly every city once. Now that has of course two properties. First of all, the length of the variable state is exactly the same as the number of cities that we have in the graph. So I can check that itself by saying what is the length of my adjacency matrix, which will in itself give 4 as a result. And the second thing is that I also need to ensure that every state or every city contains exactly once in this variable state. But I'm going to skip that for now, because if I construct the algorithm in a proper way, then maybe we don't have to be bothered by this at all. So if the length of my state variable is equal to the length of the graph, and let me just make a note here that I don't forget, make sure that there never occurs a city twice in state, then I'm going to be able to calculate the solution given this particular state, and else, well, I don't know yet what to do else, but we're going to look at that in a bit. Now, okay, let's have a look if we can code what the cost is. So typically, for example, now I could have a variable state could look like something like 0, 1, 3, 2. That means from 0 to 1. Then I have to figure out this variable for my graph adjacency matrix. Then from 1 to 3, I have to figure out this variable from my adjacency matrix. Then from 3 to 2, then I have to figure out this variable in my adjacency matrix. And then from 2 to 0, then I have to figure out this variable from my adjacency matrix. So this is exactly what we're going to do. I'm going to create a for loop for e in range length of my state, and I'm going to create a variable cost, which I initialize as 0. Cost plus is going to use the graph variable for this, state E, and then graph state E plus 1. I'm going to return now the cost. Is this going to work? It's a question, of course. We're going to test it, but probably now state will go out of memory because, or out of the range. How about I just solve it like this, and then I implicitly have to add when we have the graph going from state -1, the last variable in state, to graph 0. So this will likely work, but we only know this, of course, after we've coded, after we've tested this. Now, how are we going to test this? Quite simple. We're going to call this function in such a way that it will fall exactly into this category. I could, of course, also have created a sub-function that exactly calculates the cost. Maybe that's even cleaner. We're going to create a function that calculates cost, which gets graph and a state. This was maybe the cleanest thing. I should have done this from the start. So now what we're going to do is, here we're going to say just return calculate cost given the graph and given the state, and we can now quite easily say, let's test what the solution will be if we say calculate cost graph, and let's use the example that we have just came up with, and then this will be commented out, this will be commented out, and let's see what the solution is. Python TSP brute force, and currently we found a solution that costs 11. Let's have a look if that makes sense. We went from 0 to 1 to 3 to 2, which is basically A, B, D, C. And this coincidentally was in this list the optimal solution, which costed 11. So this seems to work out fine. Let's also try a different example. Let's calculate cost 0, 1, 2, 3, which is A, B, C, D. And let's see what happens if I type in that. And in this case, we have the value 18, which seems to align with exactly what we expect here. A, B, C, D indeed cost us 18. So this function seems to work fine. Let's continue with, let me get this bar away. Let's continue with what to do. So we now know what to do. What if we're in a goal state, but what to do if we're not in a goal state. So let's for that look once again at the state space diagram. And suppose that we're in not a goal state, and we are in a state where we have visited only one city so far. Basically what we want to do is we want to try out all possibilities and ask what would be the cost if we were to do this certain extension to the current state. And of course it seems very complex to think about what's happening in the state below in this tree, but the only thing what we really want to know is we want to figure out, suppose that we take one more step. I want to get into, from A, I want to get into the situation AB, and I will trust on my recursive function that this will somehow, once it does its recursion magic, ends up in such a state that it gets me the answer. And I'm going to trust the function itself that this will give me the answer. And this seems maybe very unreasonable, but you can see that when I'm deeper in the tree, when I'm, for example, at A, B, C, it's quite reasonable that when I add the proper city to my current state, we come into this state, and actually I'm getting an answer out of this state. So in this case, my recursion will for sure work. Now, this also means that if I do the proper things higher up in the state space tree, in the state space diagram, I will get when I trust the recursion and when I do the proper moves, I will get also the answer when I say what would be the optimal answer, or what would be the answer that we find if we add C to this state, and what will be the answer if we add D to this state. So this is actually exactly what we're going to do. We're going to try out all these possibilities. So we have currently state. State could look like, let's say we are currently in 0, and basically what we want to do is for all possible extensions to this, so for E in range len graph. So now we're going to see I is in this case once it's 0, once it's 1, once it's 2, once it's 3 in our specific example. And basically we want to add I to our state, to the end of our state. So state dot append I is going to be what I'm going to do. Then I'm going to go into the recursion. So I'm going to say current solution is TSP brute force with graph and state. And at the end, so suppose I had a state that was 0. Of course, I don't want to add 0 to this state. So what I'm going to say is I want to prevent that if I is not in state. So this way I ensure that I will only add I to my current state, that I only add a city to my current state if I have not visited it before. So that should be quite simple in itself. Then I'm going to add it to the state. I'm going to check what is the solution. And afterwards, I want to prepare my state for the next loop of this for loop. So I'm also going to remove it again from the current state. So suppose I had state 0, then first I'm going to skip adding 0 to this list because it was already in state. Then I'm going to try to append 1 to this state. I'm going to figure out what is the solution, and afterwards I'm removing 1 again from the state because I want to be ready for the next iteration of this for loop where I'm going to add 2 to this state, and afterwards I'm going to check the solution and I'm going to return 2 again from the state. And this is basically all there is to traversing this state space tree. And we can of course check whether that is indeed the case. I'm now going to remove these old test cases because those we know already. And basically what I want to show is that in case when we're here, I'm going to make it a little bit smaller so we can have a little bit more space here. I'm going to print the current state, and let's test whether I didn't make any mistakes. If I'm now running the code, I will see a list of all the goal states that we have eventually traversed. If clearly I made here if E not in state is not in state. I should have said not in state. So let's try again. Very normal to make, of course, little mistakes. This is why we keep on coding the code, testing the code all the time. And basically here I see that I've ended up in 1, 2, 3, 4, 5, 6 goal states. And if you pause the video, you can verify for yourself that these are exactly, of course you have to do the mapping between A was 0 and B was 1, but you can verify that these are exactly the same goal states as we had. And then actually I could also have put this print statement here, and then we would have seen a little bit more than we would have seen basically us ending up in every state, not just the goal states of this solution. It's just a little bit hard to induce an order from this. But basically now what we've achieved is we have traversed the entire tree, except that we haven't done anything useful yet, because what we need to do is we want to, in this case, we have this situation where we have to make a choice. We want to record, of course, what was the best choice. Now, how are we going to do this? We're going to create a variable called best choice, which we have to initialize on something. I would say initialize it on infinite, and then let's call it best solution. So basically we now have a variable that stores the best solution that we found. So far we're going to record for every possible extension what is the solution that we return. And then of course, if the current solution is better than best solution, then we're going to say best solution is current solution, and we of course have to ensure that we eventually return this best solution. And this basically is all there is to the traveling salesman problem with brute force. We can of course check whether we are coming to the proper solution. So here we're calling again TSP brute force with the initial state of starting in node 0 or node A, and kind of we expect that if we do this, then the solution should be 11. Let me double check whether I removed all the print statements, because I don't want to clutter the output. And if I now run, you see it takes Python actually a bit of a second, and then we see the solution is 11. And we could also have called it without saying we want to start in node A. I presume this will also work. It might take a little bit longer. And in this case, the answer is also 11. Of course, we can now do all sorts of interesting things, right? Maybe we also wanted to know what is eventually we now know the best solution cost us 11 units, and this is the solution that we eventually were looking for. But maybe we also wanted to know what was exactly the solution that costed us 11 units. Well, that of course would require us to not just return the value here and here, but also to return and record the state that gave us this best solution, and that in itself can be a little bit more tricky, but it's of course not that hard. And of course, maybe we want to do something that's a little bit smarter than exhaustive search, and maybe we want to do something like backtracking, that in some cases we already know, okay, this might not lead to a good solution. We want to cut off the situation early, and that of course can make the situation also, or the algorithm also, a little bit faster, especially when we're dealing with large graphs. But basically this is all there is to it, traversing a large state space using recursion, and in this case we've done this for the traveling salesman problem. I hope this helps you create such algorithms in the future.